Hello, class. I am starting this lecture for the second time because the first time I had some problems with the camera. It wouldn't focus, and I may have those same problems this time, but I think I know how to get by those problems. So, and yes, we've got a wiggly table. I've been trying to fix that too. Now, what I want to do today in this lecture is to go really through chapter 1 and to talk about some of the parallelisms and analogs between Newton's gravitational attraction. And I know I've already talked about this in Coulomb's law. What I want to do is sort of finish some conceptual underpinnings up with this. Now let's look at this just for a second. If we look at Newton's gravitational attraction law, and we look at Coulomb's law, we can see a couple things. First of all, with Coulomb's law, what if I have two charges? Let's say charge 1 is positive and charge 2 is positive. Let's just look at that first. Well, I think we all know that whether charge 1 and 2 are positive or whether charge 1 and 2 are negative, they're still going to repel one another, right? So Q1 and Q2 are going to cause a repulsion, right? Whether it's positive, I could also put slash negative, but I think you understand. Like charges repel, unlike charges attract. So what we can say here is that repulsion is positive. Does everyone see that? You know, Coulomb's constant as we looked at it here, and let's write this the right way too. Force equals Q1 times Q2 divided by 4 pi epsilon r squared. So let's write that the right way instead of using Coulomb's constant like I've got written here. But what I wanted to get to was that if I've got a positive number here and I have a positive number here, doesn't that give me Coulomb's constant is always going to be positive, and 1 over 4 pi epsilon is probably always going to be positive. I know what you're thinking right now. You're thinking, hey, are there negative permittivities? Where do you think we got the stealth plane from? I'll let you look that up. Anyway, so yeah, if this is positive, which it is, Coulomb's constant, you know, is positive, and these are positive, and then a distance, well, how many negative distances do you know? You don't know many negative distances, so, and even if it was negative, it's squared. So the quantity r squared is always going to be positive. So if Q1 and Q2 are positive charges, I get a repulsion. If Q1 and Q2 are negative charges, I get a repulsion, right? Because repulsion would be positive for Coulomb's law. And of course, attraction, let's just write that there, attraction equals negative, right? I don't know, that came through too well, but it's negative. So just so that we get that. Now, let's look at Newton's gravitational attraction again. Let's say that this is the Earth right here. Now, at the very surface of the Earth, we're going to have, a force that would be pretty great, right? All the way around here, it's going to be pretty great, strong force right at the surface of the Earth. In fact, that's where the maximum is, because we can't go inside the surface of the Earth and look for, the force, because there'll be Earth above us. There'd be mass above us, and that would be counteracting the mass below us, right? So at the surface of the Earth and above the surface of the Earth, we can figure out what the force would be. right? Because that's what we have. That's that Newton's gravitational attraction up there. You know, as I go further away, though, from the Earth, the force of attraction is going to get smaller, isn't it? Yeah, way out here, that force of attraction is much smaller. You know, what we should probably do is we should probably look and we should probably say, hey, if I take 1 kilogram of mass, if I take 1 kilogram of mass and I put it at a certain distance from the center of the center of gravity of the Earth, let's call that distance r. I'm not saying that the Earth, you know, is r. We're talking about the surface of the Earth here, right? That's what's giving us that force. And but really, off the surface of the Earth, let's say I'm going 100 miles into space. Right? Off the surface of the Earth, it's still going to give me g. Right? I just have to add that 100 miles to the 3,600 miles that's the radius of the Earth, and as you can see, that would be a very, you know, small increase in the distance. So even if I was 100 miles higher, the gravitational constant wouldn't go down except for 1/3600, or for 1/36th of 9.81. Right? Does everyone see that? Um, oh, squared, because there'd be anyway. Um, because it'd just be the different. I don't want to go through that. We sort of went through that on the last lecture anyway, but I think everybody can see that we can get different g's. G at the surface of the Earth there, and then g at r1 here, and then what if I put a larger distance out here? And then I would get another g out there, wouldn't I? And you're saying g, why is he saying g? Because what he's really talking about is newtons. You know, but didn't I say that I wanted to take a 1 kilogram? I'm going to say that this thing right here is equal to 1 kilogram. And so what I want to find out is really not what the newtons are for something, you know, between these two. What I want to say is I want to look at the Earth and the gravitational field of the Earth. And I don't even, I don't want it to be specific to how much does Scott Grenquist weigh, or how much does, you know, anybody else weigh, or how much does a Caterpillar tractor weigh at the surface of the Earth. No, what I want to find out is I want to find out if I took 1 kilogram, right? Don't you see how this sort of normalizes this all to 1 kilogram of mass? Now I'm going to take 1 kilogram of mass, and then I'm going to take that kilogram of mass and I'm going to put it on the surface of the Earth. And then I'm going to look at it at this distance r1 out here and see what the newtons per kilogram on that 1 kilogram is going to be. Then I'm going to go way out here and I'm going to say, hey, how many newtons of force now at this distance from the Earth, 20,000 miles or whatever, do I have on 1 kilogram of mass? And you know, let's say the spaceship that's out there isn't 1 kilogram. Let's say it's 1,000 kilograms. Well, then I could just take that figure and multiply it by 1,000, couldn't I? No, it's not 1,000. It's 682 kilograms. Well, then I could just multiply it by 682 and find out what the actual force would be. What I'm really getting is at every point around the Earth now, right? I can go to that point, and I know that at that point, I can figure out what 1 kilogram of mass, what the attractive force of 1 kilogram of mass would be. Now you're saying, well, newtons per kilogram. You know, newtons per kilogram, what is that? Newtons per kilogram. Well, we know that a newton is a kilogram meter per second squared. Isn't that right? Because we know that a newton is just force equals mass times acceleration, doesn't it? So we know that kilogram meter per second squared divided by a kilogram is going to equal a meter per second squared. And we know that a meter per second squared actually represents a dimension, don't we? And that's the dimension that we have right here, right? That's the acceleration. Or in our case, the acceleration toward the center of the Earth, we call that g. But remember, we want to find out the gravitational attraction at any distance r from the center of the Earth after we've gotten to the surface, of course. And that's what we've got. Newtons per meter, or newtons per kilogram, is what we've got here. But newtons per kilogram is really another dimension that we call acceleration or gravitational acceleration. Now let's go over to this equation. Let's go over to that equation. You know, when we look at that equation, F equals Q1 times Q2 over 4 pi epsilon r squared. Couldn't we do something similar to what we did over here? Instead of finding out the force, let's find out the force for a charge, just like we found out the gravitational attraction constant of the Earth, and then that's really newtons per kilogram, right? Let's do the same thing over here, but instead of finding out newtons per kilogram, there's no kilogram in here, let's take one of these. Isn't that what we did over here? Didn't we just take one of those and then we just normalized it to to 1? So we're looking at 1 kilogram. Doesn't this always have then 1 kilogram the denominator? It sure does. And you know what we've got over here when we look at force? What if we said, hey, well, I want my force per coulomb. Force per coulomb, because isn't charge in coulombs? In fact, what I'm going to say here is that this Q2 is really 1 coulomb. And then I'm going to normalize it for down here, and I'm going to say, hey, force per coulomb, that would be newtons per coulomb. I suppose I should put force per charge. Now put charge sub 0 because we're saying that's 1 coulomb. So newtons per coulomb would equal Q, whatever charge particle that we have. Let's say, just like that, instead of the Earth, I have an electron, right? What if I've got an electron down there? And then I could say that, well, this is the charge on the electron, minus 1.602 times 10 to the minus 19 coulombs, divided by 4 pi epsilon r squared. And then what I would get is I would get newtons per coulomb. Just like over here, I got newtons per kilogram, right? Newtons per kilogram. And we knew that newtons per kilogram was meters per second squared, and we thought, oh my God, meters per second squared. That's got to be the gravitational attraction of the Earth, right? I see how it went out of focus? I've learned now. I just tap it. Now, let's go down here and see what we've got. So, that's newtons per coulomb. You know, when we think about newtons per coulomb, well, a newton, that's a kilogram meter per second squared, and then a coulomb, we know, is an amp second, isn't it? Right? That's the combination of primary units that make up both a newton and a coulomb. So, you know what we could say here, that this is really a kilogram meter per seconds cubed amp. Oh my God, a kilogram meter per seconds cubed amp. What does that look like? Well, you know, a volt, let me continue this down here for a second. You know, a volt is a kilogram meter squared per seconds cubed amp. I want you to realize as I'm going through and doing this dimensional analysis too, that this is something that you should keep in the back of your head and always take with you to whatever job, that's an S by the way, you go to, and understand these things, right? Some of the most important things is the dimensional analysis for you to see how to limit experimentation and everything else. Dimensional analysis and similitude. All right, let's go back to this. So I think everybody can see then that what I've got up here, really a kilogram meter per seconds cubed amp is really a volt per meter. What is that thing? Oh, it's a light. I don't know. Anyway, it's a volt per meter. How did that light get in there? What the? It must be reflecting off something. Anyway, that's right. And volts per meter, you're thinking to yourself, a volts per meter, well, I don't know any dimension that really is in volts per meter. Yes, you do now, because volts per meter or newtons per coulomb, let's circle both of those because it's a newtons per coulomb, but it's also a volt per meter, isn't it? It's a volt per meter. You know what a volt per meter is? A volt per meter is an electric field. Volts per meter is an electric field. Just like in the Earth, we've got a gravitational field, and that gravitational field is really an attractive force field, isn't it? Because gravity only works one way. It works as attractive. We don't have gravity that's repulsive. Actually, in the universe, there is repulsive gravity, but that's a whole different graduate course that you're going to take. Now, let's get back to this. So, with gravity, it only goes one way, but with electricity, or I should say electromagnetic forces, it goes two ways, because we can have a point charge that's attracting things, and we can have a point charge that is repelling things, right? And by things, what do I mean? I mean a positive one. You know, when I'm saying 1 kilogram here, I really mean positive 1 kilogram. And you're thinking, well, how could it be a negative 1 kilogram? Well, that's right, it couldn't be, right? Because we only know positive mass so far that you're familiar with. But over here, we can have positive and negative electric charges, can't we? So we can have something that's repulsive or attractive. So if I was going to make up an electric field, what would an electric field be? Let's say that I had something that was positive, like a proton. So I have a proton down there, and that's a positive force. So if I put a positive in for Q, everything else in here is positive, right? And why is this a positive or a repulsive force for this positive charge that I've got here? I'm saying it's positive everywhere, and you're saying, well, no, it's not, Professor Grenquist, because if an electron was traveling through here, it would be attracted. So why is it positive? It's positive because we're always thinking positive. When we're thinking of a 1 kilogram over here, we're thinking of a positive 1 kilogram. If we were talking to aliens from another planet, and the aliens brought up the fact that there was negative matter, then we would have to take that into account, wouldn't we? Come on, get back to, there you go. So, but we don't know that there's negative matter, but we do know there's negative charges. And so we're always assuming that whatever we're looking at, the electric field around here, our candidate charge is always a +1 Coulomb charge. So we're looking how a +1 Coulomb charge would be affected. In fact, we're looking at what a +1 Coulomb charge, the force that would be on a +1 Coulomb charge if it was at a certain distance r from that proton. And isn't that what we're doing over here? Aren't we looking at the force that would be on a 1 kilogram? Isn't that what we normalize this to? That's the force that would be on a 1 kilogram mass at a certain distance r from the center of the Earth. Same thing here, a +1 Coulomb charge. So if you ever want to think of the difference between an electric field, I'm going to sort of leave the gravitational analog behind now. If you ever want to think of what is the electric field for a particle, what you really want to think of is what is the force between that particle, right, and a 1 Coulomb charge inside whatever dielectric epsilon represents, because that's the dielectric constant, right? Well, I forgot to turn my timer on, so I guess that's fine. So this would be the force here, but we can write that same thing if we're looking at, and of course the force has direction. These are all becoming vectors now, you know, and this would be in toward the center of the Earth. And if I'm looking at the, oh, I'm sorry, that's my electric field. Oh, no, I'm sorry. Oh, where is that? I had it here someplace. There it is. Yeah, that was my force. Oh, wait, wrong one. That's my force, not my electric field. But my electric field, of course, is going to look just like it. It's going to be Q over 4 pi epsilon r squared, right? And the electric field is always in the same direction as that force would be. Okay? So we're gonna get more into that. I'm just trying to, you know, introduce the concept and let you see the concept of how I go from the Coulombic force equation over here to the electric field equation over here. Always remember, it's that 1 Coulomb charge, just like we use the 1 kilogram charge. It's the 1 Coulomb charge that we're using there, and we got all the forces of. Now, I want to also define some things that we're going to be talking about over the course, and they're in chapter 1 too. Two things, and I'm going to use an analogy to magnetism here too. So I want to bring out the analogs in many ways between electricity and magnetism, and also talk about the differences between electricity and magnetism too. And I think immediately the first thing that you realize with the difference between electricity and magnetism is that electricity has a positive and a negative, right? And I can separate those charges. I have a charge, an electron, that represents a negative elementary particle, right? In magnetism, we have no parallel. There are no independent north poles. There's no independent south poles. There's no independent any poles. Whereas in electricity, we do have the independence of those independent negative and positive charges, don't we? They manifest themselves in different ways too. So let's talk first of all about the language that we're going to be using. So if I use E, and I'm talking about an electric field, when I use E, I'm really talking about without the vector on top. Well, let me do this. Let's say I'll put the vector on top, and that's called electric field strength. The reason I'm taking some time here is that there's people use different things interchangeably, and older engineers use some terminology for these that younger engineers don't use, that newer textbooks don't use, and I want to explain it to you because it's almost like a quantum step from guys who came through prior to 1970 and guys that came after 1970, it seems. Or maybe it was 1980, can't remember, but electric field strength is what we call the vector. Now, the magnitude of the vector, this is just the magnitude, and this extends to other things too, and I want you as professional engineers to, understand the difference between the two. This would be electric field intensity, right? See how you see the difference that you're referring when you're referring to the vector, you're talking about electric field strength because you're talking about like velocity, right? Velocity is not only speed, but it's also speed and direction. If I'm saying I'm going to New York at 60 miles an hour, that is velocity. If I'm saying I'm going 60 miles an hour, that is speed. Same thing is true here. Electric field strength is the vector. Electric field intensity is the magnitude of the electric field, just the magnitude, the scalar value of the electric field strength. All right, we got that out of the way. Here's another variable that we're going to be using a lot, and that is D. And D also is a vector. It's called the electric field flux density. Now that's what we call it. The younger engineers call it that. Older engineers, for some unknown reason, call it either the dielectric displacement or you'll hear some just refer to it as the electric displacement, right? But I just want to point those things out to you. Now we're talking about electric field flux density, so that means that we're also talking about electric field flux. Well, I'll tell you what flux is. The flux for an electric field is charge, right? And so you're probably saying, well, okay, well, electric field flux density. And when we say electric field flux density, what we're really talking about is, let's say that I've got a piece of wire here, right? I got a piece of wire, and it's got a cross section, right? I just taken a wire loop like a coat hanger, made a wire thing out of it, and it's got a cross-sectional area, right? So there's this cross-sectional area, and the wire, the length of the wire, let's say the wire starts there and ends there, that's just going to be equal to, if it's circular, that would just be equal to the circumference. Why don't I just put 2 pi r? You know, I'll say it's a circle. Oh, can I come in better? I don't know. I'll tap it again later. All right. So let's say that I've got that, and then let's say that I have flux charge, right, that is flowing through that opening, right? Bunch of flux is flowing through that opening. That would be my flux density. So flux density is going to be in coulombs per square meter. So there you go. We've got a couple things here then. So let's just write these down sort of to keep track of them. So we've got electric field is in volts per meter. Electric field flux density is in coulombs per meter squared. And then my flux itself is going to be in coulombs. So there you go. got some of that terminology out of the way. And I want to point out, so let me put this here for a second, because now what I want to do is I want to talk a little bit about magnetism. So if this is our electric field strength, and you probably saw in the very last page, I think it was, no, it was page 15 in the textbook, that D equals epsilon E. Let's put a little box around that. D equals epsilon E. Where have I seen something like that before, where the flux density equals some type of constant times the field strength? D flux density equals constant times the field strength. And you're probably all saying, well, of course, that's B equals mu H, isn't it? That's B equals mu H, very similar to that when you were doing motors and controls, the magnetization curve. And if I was to look at the magnetization curve for a couple different things, I would, let's just look at a BH curve, right? So if this is B, this is H. Now, if I look at a BH curve for most things, it would look something like this. It'd be way down here, wouldn't it? And isn't that right? Because usually when we think about mu, just like the way we thought about epsilon, there's a relative permeability times an absolute permeability, isn't there? Mu, B equals mu H, mu, relative permittivity, absolute. And we know that our absolute permeability is 4 pi times 10 to the minus 7 henries per meter, right? Oh, you know, over here, I'll just stick this down here again. Epsilon sub 0 equals 8.85 times 10 to the minus 12 farads per meter, right? So we have those two constants. And we know for both of those two constants, like for instance, for a material, let's say that a material I'm thinking about is mica or glass. I know that the permittivity for that material is going to be the relative permittivity, which is a ratio, like I said in the other lecture, times the absolute permittivity. Same thing is true for this. The permeability is the relative permeability times the absolute permeability. So most things have a relative permeability equal to 1. And that puts them way down there. But we know with steel, right, that steel looks like this. And right here, look at that slope of that line. Look at the slope of that line as compared to the slope of this line. I haven't exaggerated. I should have drawn that straight up, really, for steel, right? Not drawn to scale. There's my disclaimer. But for steel, mu sub r equals 1,000, right? Mu sub r equals 1,000. Do we have something like that for epsilon sub r? We sure do, right? Or how could we make capacitors? That's right. We've got something like that for epsilon r2, and I'm going to talk more about that. But look at this curve here. There's B, there's H, and this would be mu. And so for steel, when we look at it, we say that B equals mu sub r for steel times mu sub O times H, right? And that's why steel is so good for using in magnetic applications. And we've got something very similar to that to use for capacitor applications, don't we? I'm going to hold it there because I'm going to switch to another page, and hopefully this time I'll even turn on my timer and find out if I've actually done this correctly or not. But let's go on. Okay.